All right. So in the past two lectures, we discussed the emergence of quantum field theory or field theory in classical statistical field theory in classical and quantum physics. So if you view this as a length scale, you could have short length scales. We're going to refer to them as ultraviolet or UV, or very long wavelength or infrared. Quantum field theory appears in very long distance or very long wavelength. As we said, when you look at the collective low energy excitations of systems, or quantum field theory could arise as deep in the ultraviolet, when relativity is the symmetry of the theory. And this is the context that's often discussed in high energy physics. This is the context that's often relevant for condensed matter physics. However, there is no clear cut between these two fields anymore, condensed matter and particle physics. So today we're going to be talking about where do quantum field theories of the infrared come from, and we're going to work out an example. This is a theory where the ultraviolet degrees of freedom are sites of as a solid. It's a solid. It's a collection of atoms, and in long distances, a field emerges, which is a sound field. We're going to work out this example in detail, in gory detail, and see that we're describing a many-body system of particles. We're going to solve it. We're going to find collective excitations, quasi-particles that I've mentioned in the past. Here, the name that goes with them is phonon, quanta of sound. We're going to take a low energy limit and see that the relativity emerges in the infrared. And we get a quantum field theory, which is a free scalar field theory. So this is some set of words that I said in the past two lectures. We're going to see an explicit example of that today. All right. So we're going to work out the simplest example of quantum field theory we could discuss for today as emerging in the infrared limit of a lattice model. We're going to see that actual relativity is also emergent in this example. Questions? All right. So sound. What is sound? Sound is the infrared field of solids. Consider a metronome or a tuning fork. Actually, not a metronome, a tuning fork. When you hit it, it starts vibrating and creates sound. What is sound? If these are the atoms or molecules of the tuning fork, or air actually, they are considered the tuning fork. So they sit in a solid with some distance. There are these collective motions where the atoms become closer and farther, closer and farther. In their equilibrium, before you hit them, they're sitting on a lattice in an organized way. So let's say it's a lattice. And as you hit it, as you create sound, it creates this compression, stretch, and this wave propagates down the solid, right? So we're going to model this. So we're going to model it this way. To simplify it, consider a system of atoms sitting on a one-dimensional lattice, right? So each of these guys represents an atom. Now, there are pairwise nearest interactions because atoms if we're going to model it this way, if they pull them apart, they're going to attract. So there's the equilibrium position. If you pull them further out, they're going to attract. And if you push them closer, they're going to repel. So to model this, we're going to imagine a whole bunch of masses attached with strings. So in equilibrium, these are equidistant from each other, and the strings are not in their equilibrium distance. And excitation corresponds to changing or moving each of these particles from the equilibrium value by some amount that we call Q. So the ith one is moved from its equilibrium. So let's say the equilibrium values are just like q x minus 1, xi plus 1, and so on and so forth. And the distance between them, say, is epsilon. This is the equilibrium distance, right? So when you perturb the system, when you pull it or hit it, right, each of these atoms is going to get displaced by some amount q. So we're just only going to keep track of the displacements from equilibrium. All right. So if the displacement is, this picture should be clear. If the displacement from equilibrium is very, very slowly side to side, the picture you have is some sort of a wave, right? So this is a sound wave that we described. This is like a, in very low energies, this is a sound wave we're going to be talking about. This long wavelength. So by now I've drawn a couple of times this picture of some degrees of freedom. We talked about the XY model when these spins align together and very slowly feel. So we're going to make this more quantitative. This is a many particle theory of solids. So let's just, for simplicity, put them on a circle, right? So the circumference of the circle is n epsilon. N is the total number of atoms. And the distance between them is epsilon. We're going to take n to be a large number. We're going to assume each of these particles to have mass m. And then, of course, the nearest neighboring interaction, we're going to model it by potential that depends only on their distance, right? So V of Qi plus 1 minus Qi is the potential that they feel pairwise. So as we said, the equilibrium is where these positions, the difference between them is just epsilon. Actually, no, I think in the convention, oh, okay, sorry. Yeah, here I'm using convention where Q is not the displacement from equilibrium per exact. No, actually, that's correct. No, that's fine. That's fine. All right. So I should probably say these are x's. Oh, this is a PDF actually. Yeah. All right. So let's go with this. All right. So what's the Hamiltonian? The Hamiltonian for the system is pi squared minus 2m. This is just a kinetic term for each atom plus half lambda of qi plus minus qi over epsilon squared plus higher order term. So what have I done? I've just taken the potential, right, and expanded it order by order in distance, right? Now, could there be, so there could be a constant term. The constant term just throw out because it shifts the energy. Could there be a linear term? Could there be a linear term here? Any question? Any thoughts? Why haven't I included a linear term?
So that would mean that there would be a constant force at equilibrium, but that can't happen.
So equilibrium means what? Means minimum of the potential, right? So it means that the first derivative will have to vanish, right? So when we say it's equilibrium, it means that the first derivative will have to vanish. Therefore, it will start on the second derivative. And for simplicity, in some small variation, expansion, because I said this long wavelength, right? I've just expanded to second order. I only obtain the second order term. Of course, all the higher order terms will have their own coefficients. I'll just keep track of lambda 2 that I call lambda and set the rest of them to 0 in this approximation. We come back to including interactions. These higher order terms we're going to call interactions for n larger than 2, right? So these are more complicated interactions. Is the model clear? All right. So this is a classical system for now. Let's first solve this classically. Then we're going to come back and quantize it. So how would you solve this? In classical physics, you've learned that to solve this, you have to diagonalize the Hamiltonian and find the normal modes. Right? This is not diagonalizing the Hamiltonian in the quantum mechanics sense of it. You just have a bunch of harmonic oscillators that are coupled. you have to diagonalize the Hamiltonian in terms of the right classical variables. So this Hamiltonian, if you stare at it for a bit, you quickly realize that you could diagonalize this Hamiltonian using Fourier transform. So if that's not very clear to you, here's the explicit way of doing it, and just plug it in. So this is discrete Fourier transform on a circle, right? So introduce Q of K, which is the Fourier mode associated to Q of J. J is the site. I was calling it Q of I, but so that we don't get confused with the square root of -1, I'm just calling it Q of J. So it's sum over J from 1 to n with these phases, right? And this is normalization I've used to define the Fourier transform. It's just discrete Fourier transform. You Fourier transform both the position and momenta, because this is in classical physics, Q and Q dot or conjugate momentum. Conjugate momentum are the variables you have to define, or you have to specify to determine the evolution, right? Okay, good. So this is the transformations. Every time you're trying to solve one of these systems, a many-body system, the first thing you should do is try to look for symmetries. A lot of this course is going to be about symmetries. So on a lattice, the symmetry that you have is translations, right? So actually using, maybe I shouldn't over-explain, but from the translation symmetry of the lattice, you could have guessed that the thing that diagonalizes the Hamiltonian is Fourier transform. But okay, well, I'll leave it to you guys to work this out for yourself. All right, here are the transformations. You just plug them back in the Hamiltonian that I had written. You end up with a sum over the momenta, right? Pk, P minus K over 2m plus half m omega K squared, Qk, Q minus K. Now, this is diagonal because all the terms involve K. And here we had I and I plus 1, right? So this was not diagonal. This was tridiagonal. This term is tridiagonal. And then we just diagonalized it using Fourier transform. So if you just keep track of everything term by term, you realize that the normal modes end up being 2 square root lambda over m. Lambda, do you guys remember what lambda was? It's a spring constant, right? It's like a spring constant. Square root of lambda over m, sine of absolute value of k, epsilon over 2. Why should there be an epsilon here? Because momenta, first of all, inside the sign, you should have something dimensionless, right? So momentum has a dimension, and in this example, the natural units of momenta are going to be 1 over epsilon, right? So k epsilon is a dimensionless parameter that would just sit here. You could guess that by dimensional analysis. All right, so what this has a name. This is dispersion, right? This is the dispersion relation. All right, let's plot the dispersion relation. And what we're gonna do is we're gonna compare omega of k to omega of 0. Right? Is the idea clear? Because omega of 0 is the energy that corresponds to the mode with 0 momentum. Omega of k is the energy of the mode with momentum k, right? How does adding momentum change the energy? That is called the dispersion relation. So this dispersion relation is discrete. Here it is, k epsilon. We're going to plot it here because the values of k are discrete. Why are the values of k discrete? Because it's discrete Fourier transform, right? I took n number of sites. And if you make this plot, you see that this dispersion relation looks linear near 0. And then it grows and it flattens out. It becomes like this. It doesn't actually flatten out. It turns out and comes back. So this dispersion has a whole bunch of properties. First of all, if you take omega of k, if you take omega of k and take a k derivative of it, what is that thing called?
Like a Taylor series?
No.
What do you mean?
So there's a group velocity and phase velocity. This is just wave dynamics. So yeah, it's good to think about what we are doing here, right? So this is the dispersion relation. If you look at the tangent here, that is that's which one is it? Is group velocity. The tangent here is a group velocity. So the tangent is basically the velocity. Here near zero, which is low momenta, which is long wavelength, right? You see a linear dispersion. So what does that? So there are two interesting features of it. First, there is a maximum energy for momenta in the dispersion relation. And second is linear here. All right, so we're going to come back and comment on these two features. Let's work out the equations of motion. So the equations of motion are the Hamilton-Jacobi equations of motion. Del T of Q of K is the Poisson bracket of Q of K and H, which is P of K over M, and del T of P of K is just this. Does everyone know what the Hamilton-Jacobi equations are? Hopefully you recall from classical physics. If not, just read the Wikipedia page on it, or just go back to your undergraduate classical mechanics textbooks. All right, so these are the dynamical equations of motion, right? Okay, so what do they give us? When you try to solve the equations of motion, you find that m del T squared of Q of K is minus 2 lambda, 1 minus cosine K epsilon Q of K, right? So it's more natural for me to divide this by m and put lambda over m here. Do you know why? It's just dimensional analysis, right? These are inverse powers of t, and lambda over k is like omega squared. So that's like inverse powers of t squared, right? All right. So as we said, you Fourier transform your Q of k's and plug them in here, and that diagonalizes the equation. You obtain the following simple algebraic equation. So previously, what we did was we Fourier transformed Q J to Q of K. Now we're Fourier transform in time. So we're looking at frequencies, right? So we Fourier transform in space and time. Is that clear? We're going to see that in quantum field theory, we do this all the time. We Fourier transform in both space and time. Actually, I should pause here. Are there any questions so far? So what we're doing is that we're solving for a system of like a bunch of mass points attached by springs, and we wrote down the potential, and in the limit where the fluctuations or the displacement of each mass from equilibrium is small, so that we could approximate this with long wavelength physics.
This transform just it's like the inverse Fourier transform of the one we did previously, right? Just to be clear, or is it something different?
No. Previously, what I did was I Fourier transform in X.
Oh, I see.
Now I'm Fourier transform. So when I did, so look here. So here I clearly have time derivatives, PIs, right?
Mm-hmm.
Here, if I look at this is like the space derivative squared, second derivative, yes. Right? So first I Fourier transform in this variable, then I Fourier transform in time, right? But I did it separately because I just wanted to show you step by step what's going on, right?
Okay.
Time is continuous here,
yes.
Right? Whereas Fourier transform in space is discrete. That's why I did them separately.
I see. But this one, so why is this not an integral then?
Oh, this I can write as integral, sure.
Okay.
Yeah, I can write as integral. I just wrote as omega. Well, you could tell why actually. In a second, you could see. Yeah, because only the
I see. Only like the resonant modes are being
Yeah,
summed
the only-
over. I see.
It ends up being a bunch of points. But in
Okay.
principle, I should do it as an interval, and yeah.
I see.
All right. So the algebraic equation becomes omega squared minus omega k squared q of k omega equals to 0. Right? So this is the algebraic equation that we obtained, which recall what omega k squared were. Omega k squared were here, right? 2 lambda of 4 lambda over m sine squared of k epsilon over 2. All right. So as we said before, if you look at the proportionality constant between omega k and k, this is at low momenta, this becomes linear, and this is just speed of sound, the speed of sound propagation, right? We said that in low energies, what you have is sound propagating, and this v of s is nothing but the speed of propagation of sound. Good. Yeah, I said this, right? So these are the sounds, so you could think of them as compressions, stretch, compression, stretch, compression, stretch. Any questions? Sorry, I think your audio is very low quality.
Sorry, so the last equation is just saying that we only have waves that move the sound speed.
I cannot hear well. Is it me or the audio quality bad?
I can't understand Alan either. I
Can you
think
type
maybe
it in the chat, please, your question? Can you type your question in the chat? Meanwhile, are there any other questions? All right, please type your question in the chat because the audio quality was very low. Could not hear. I could not understand. All right, I'll start talking, but once the question pops up, we'll address it. So, in summary, what we did so far. Oh, okay. I was asking if the omega difference equation is saying that the wave can only move exactly. Very, very good. Exactly. So this omega equation says that each momentum mode moves with a particular frequency, right? So, all right, here. Okay, this is, what is the dispersion relation like? It's like sine, right? So if you have a k, it uniquely tells you about the energy that corresponds to it. However, for fixed energy, there are many modes, different modes. So it's, for each k, the speed of propagation is fixed, right? Different frequencies will, different momentum modes propagate with different speeds. Actually, here's a nice piece of physics. If you have a medium where all momenta, all k's propagate with the same speed, then sound propagates pretty well. So on the other end, if I say something on this side, on the other end, people understand. But if the medium is such that the speed of propagation depends on the mode, if I say a word on this end, on the other end of the solid, it's very hard to understand because every signal has different Fourier modes. If different Fourier modes propagate with different speeds, on the other end of it, you're going to get a mess, right? So medium that propagates, sound propagates really well, is a medium that the speed of propagation is independent of the mode. It's just like some physics that could be helpful. All right, good. So this is the classical story of it. This is the classical physics of it. What we're going to do in the remainder of the lecture is to quantize the system. Good. So hopefully the waves are clear, the fields are clear in the low energy. So recall that in the UV, in the ultraviolet, degrees of freedom that we discussed were distinguishable particles, right? Each of the atoms, those were the degrees of freedom in the UV. In the infrared, we got these sound waves. We're gonna see that once we quantize the system, these sound waves actually end up being bosons. So they have statistics, they're indistinguishable. They're gonna correspond in the quantum world. They're gonna correspond to some emergent quasi-particles, and their dispersion relation is going to be, they're gonna be indistinguishable. They're gonna be indistinguishable, and they're gonna propagate with the speed of light, very low, speed of sound with very low energies. All right, so they're going to be relativistic. We'll see. All right, so we're gonna quantize this. Once again, I'm gonna ask questions. Is everything clear so far in the classical physics side of it? This is the simplest field theory that we're quantizing. Of course. All right.
Sorry,
So, yeah.
I have a question. We can say something about the high momentum limit or nothing?
Oh, you're saying that no, it's just they oscillate. They just oscillate, right? Like there's no large sorry, maybe I did not understand your question.
At high momentum, we can say something about the system itself. Yeah. Can we say something or no?
Well, we know everything about the system, right? The theory that we wrote down is Gaussian. So what is the question you're asking about the high momentum modes? We know it's dispersion. Just plug in. We know the speed that it propagates with, right?
Okay.
Yeah, every aspect of it is like we've up to here without any higher order interactions, only with the Q squared term, we solved it. This is just a full solution. Like we just plug in. What it is a bunch of waves propagating at different with different velocities that you could read off from the plot.
All right.
Actually, like, I don't know if this is super relevant, but like, what does a negative group velocity mean in this context?
Oh,
Because like you can see it like when it turns around, the group velocity becomes negative, right?
it's propagation in the opposite direction.
I see.
The absolute value, the modes, yeah, it is a little bit tricky because but it's basically propagation in both directions because sound can propagate in both directions. It's more meaningful.
I see. Just because like if you have the negative k vector, like you're propagating in another way, but somehow as you increase it.
So if this were in higher dimensions, I would be writing vectors of k vectors, right? And then v would be a vector. This velocity would be a vector. Here we're in one dimensions. I didn't bother to view it as a vector, but of course it has the sign.
Okay.
Which tells you about the direction of propagation.
I see. Okay. Thank you.
Sure. All right. So let's quantize it. We saw that classically, the low energy excitations are waves. Using the wave particle duality, so there's no particle picture classically, right? Now, using wave particle duality, we said that waves and particles quantum mechanically are the same thing, really. The quanta of sound, we're going to call them phonons. Okay, so how do we quantize this? The classical degrees of freedom Q and K, these are generalized coordinates and their conjugate momenta. We promote them to operators Q hat and P hat of K. Because we already know that the Fourier transform decouples various modes. So we're gonna start with the Fourier transform Hamiltonian. this is the commutation relation that we imposed, right? This means that P and K are canonical conjugates, right? P and Q, sorry, P and Q. I apologize that I'm now using K as the label. Well, I think the context is clear. I don't, maybe I don't apologize. It's all good. All right. So for a second, ignore the K equals 0 mode. Okay. Ignore the K equals 0 mode. I'm going to write down a Hamiltonian as a sum over K of 1 over 2m pk p minus k plus m over 2. Now these are operators. Omega k squared q k q minus k. This is nothing but a collection of decoupled simple harmonic oscillators. You're quantizing or whichever quantum course, any quantum course that you've ever taken has definitely quantized this in a million different ways, right? So because we went to the Fourier space, we decoupled these modes. Now it's just a collection of harmonic oscillators, right? K and K prime are decoupled. They don't appear in the Hamiltonian. So we have diagonalized it. That's what we meant by diagonalizing the Hamiltonian classically. By the way, just something for you guys to think about. Why is this K and this is minus K? I think this is something that you have to get over and think about and understand now, because in every equation in field theory we write down, K and minus K will sit right next to each other. So it's important that you understand this aspect of why is this K and minus K. All right. So how do we solve this? We usually, the simplest way of doing it is to define creation annihilation operators for every K mode, right? And then these are the corresponding commutation relation between the creation annihilation modes. So here's the creation, and here's the annihilation. Sorry, here's the Q hat and P hat in terms of their corresponding creation annihilation modes. Now, once again, I encourage you to think about why this is minus K and this is K. A hint is the fact that think about Q hat as an operator is a self-adjoint or not. So these are, from time to time, I have these like whatever this color is, this like light purple color. These are things for you guys to think about. I don't want to like chew everything and put it in your mouth. Like I want you to think about some of these questions on the side, right? Every calculation has many different aspects you could think about. All right. So good. Once you define creation annihilation variables, now your Hamiltonian is sum over k h bar omega k of just a Hamiltonian simple harmonic oscillator. So you have a collection of simple harmonic oscillator. If you recall, every simple harmonic oscillator has a frequency, and here's the list of frequencies, omega k's. We said there was a plot that we had, sine of k epsilon, that was telling you about how the frequency depends on k. We said that we ignored 0 mode. Let's put it back in. Do you guys know the physics of the 0 mode? I've written it right below it, but what is the 0 mode?
Like everything moving in the same direction.
Yeah, it's a setup where, no, not in the same direction. It's a setup where all the particles are in the equilibrium values, but they all move together. So they are in equilibrium. Equilibrium means their distance is epsilon, fixed. You take this and just rotate it, right? So this is a 0 mode. Anyway, I'll not, yeah. Okay, good. So, yeah. So this is a quantization. Good. So a simple harmonic oscillator, hopefully you recall the Hilbert space. Now, what we're gonna do is the Hilbert space of this, of course, you know, is is a Fock space, meaning that for each A of k, you could have 1 excitation, 2 excitation, 3 excitation, and arbitrary number of excitations. So let's consider the single particle Hilbert space. Okay. So first, let's start with the ground state. What is the ground state? The ground state is the of each harmonic oscillator. You know what it is? It's the lowest weight state. It's the state that's killed by A of k. Now, the zero particle Hilbert space is one-dimensional. It's the tensor product of all ground states for each k mode, right? So basically, this is a state that is killed by all AKs. This is the zero. This is a ground state. It's unique, and it has yeah. How much is this energy, by the way? Any thoughts?
P0 square over 2m.
So each harmonic oscillator with frequency omega k, what's the vacuum energy of a simple harmonic oscillator?
Of h cross omega.
H bar omega over 2, right? So each
Professor,
mode,
sorry, wouldn't the AK times the vacuum be 0? Not ket 0, just 0.
oh, I'm sorry. Thank you. Yes, of course it's 0. Thank you. That's a typo. Thank you. Yes. Yeah, so the vacuum energy is half h bar omega k. Now you have a collection of these guys, so the vacuum energy is sum over k half h bar omega k, right? Good. So the single particle excitations means that the Hilbert space you obtain by acting with AK daggers on omega, right? So now there are different single particle states you could have. They could have different momenta, right? So if you have a, you could have a single particle in single particle momentum k1 plus like superposed with a single particle of momentum k2. If you act with 2 A daggers, that's a 2 particle state. But you could act with 1 A dagger of k1, create a 1 particle state, superpose it with the state with another particle. So in particular, you could take AK dagger acting on omega, Fourier transform it. This is just superposing, right? Like these are sums of the kits. This is still a vector in the 1 particle Hilbert space, and from Fourier transform, this means that this is a single particle inserted at point xj, point on the lattice. So the 1 particle, single particle Hilbert space is the span by these guys, right?
One question, Professor, sorry.
Call me Nima.
When you define the global vacuum as the tensor product of K vacuum states,
Yes.
and you apply an annihilation operator on the K vacuum, how do
Yes.
you express it when applying it to the global vacuum? So the operator goes to its non-trivial, or
Sorry, you're asking what is this? This is 0.
yes, but how can you express it with the tensor product? So the annihilation operator goes to the non-trivial side, or
Yeah. Well, each of these guys. So yeah, I write it AK, but what this operator is just like, so here, this is A of K1 tensor, identity of K1, identity of K2, identity of K3, and all the way until some mode that I'm calling K, where it's A of K, right? Tensor da da da.
okay, thank you.
Just writing it this way, because this is a complicated notation, right? It's like, think of it this way: if I have a spin system, right? There's a spin degree of freedom at each side, and this is side 1, 2, 3, 4, 5, or something. I can talk about sigma x at side 2, acting on the Hilbert space. I don't have to necessarily write identity, tensor this, tensor identity, tensor da da da. I just write this, right? It means the same thing.
Oh, okay, thank you.
Good. I mean, this notation is very common. I mean, it's almost is inevitable when you're dealing with multi-particle systems, right? This is exactly the multi-particle aspect of it. It's multi-particle, so I have to use this notation. Otherwise, it's just impossible to keep track of. All right. Any other questions? So I absolutely I encourage you guys to think about how does this Hilbert space, this single particle Hilbert space, compare to solving the Schrodinger equation for a particle on a circle. Good, let me repeat. What did we do? We started with a set of, this is a multi-particle system, right? And there was a degree of freedom at each site, which was, it was an atom, right? We solved the system, we quantized it, it's just a bunch of harmonic oscillators. We consider one particle Hilbert space. It's a subspace of single particles. You get something. I want you guys to compare this answer you get with a single particle, quantum single particle, free particle on a circle. But this is something that do for yourself. You're gonna see learn some interesting stuff. All right. I'd said in the past many times that quantum field theory is inherently a multi-particle theory. So what we have is a Fock space. So we have all the particles all at once. I can have a two-particle state by acting with A dagger K1, A dagger K2. I can have n particle state. I can create nk1, K1 particles, nk2, K2 particles, and so on and so forth. A good notation for it is to write it this way in terms of the eigenoperators of the number operator, right? This is the number operator that counts the number of phonons of momentum k. Good. Now, if you recall, we said this was the commutation relation, which means that AK and AK dagger, AK dagger and AK prime dagger commute. That means the system is bosonic. These are indistinguishable particles and they commute. Their wave functions must be symmetrized. The phonons are quasi-particles. In terms of the original degrees of freedom, which were these masses, the masses were distinguishable. They had different statistics. They were very different things. They were massive, for one thing. The quasi-particles we find in the low energies, phonons, these are emergent particles, and they're indistinguishable. So all the multi-particle wave functions need to be symmetrized because these are multi-boson states. So you take the Fock space. The Fock space is the zero particle Hilbert space, which is one-dimensional, right? Oops. It's basically this guy. Then you have the one particle Hilbert space. You know how to construct it. We constructed it. Two particle Hilbert space. You can imagine how it works, right? Any thoughts on what the two particle Hilbert space will look like? So you just have to superpose these A dagger K1, A dagger K2s. And yeah, it's like a bilocal operator, right? It creates a pair of excitations at different points.
So is it like your basis vectors become like the permutations of, or like the combinations, a combination of like 2 choose n or whatever? where N is the number of total nodes. I don't know if that's clear.
You could, well, there are such, there's so,
There's
what
like
you're
two
saying
choose
is
N basis vectors
choose
in
two, there's
H2.
N choose
Or
two
N choose two, sorry, right,
N
yeah.
choose two terms you could write down.
Yeah,
right?
and those like are your basis
But the-
vectors that span the Hilbert space.
You could use that basis. You could use that basis, but what I wanted to point out, I wanted you guys to compare the two particle sector of the Fock space to two bosons. This is quantum mechanics living on a circle. Quantum mechanics of two bosons living on a circle. I wanted to make that comparison. Previously I said compare the one particle Hilbert space to one particle living on one particle living on a circle. Now, because this boson is two bosons, right? Yeah, what basis you choose is there are many different bases you could use. Any questions?
So when we call these particles, like physically they don't like, they're still, how to say, waves?
No, I Fourier transform it. This is exactly what I did. I Fourier transformed this.
Oh,
I got a dagger of xj. I called this a single particle at point xj.
But these, like this xj is not the one
It is a site.
associated with the ladder operators.
No,
Like
this
there,
xj is a point on a ladder it's a site around the circle.
yeah, but it's a superposition of a k.
Sure.
So like when we
So the
when we
same way
do
that-
this, when we do this like this operation on the Fock space, like the
so make this
states you
compare.
generate, like the states you generate are superpositions of waves. Or
Yeah.
am I misunderstanding it?
Think of no, that's good. That's good. Think
Okay.
of psi of x as being an integral or sum. If it's discrete, sum over k e to the power of ix psi of k.
Mhm.
Right.
Mhm.
This is the wave function in momentum space.
Mhm.
This is the wave function in position space. That's what we're doing.
Yeah, but just to clarify, like the AKs are in momentum space, not in position space.
Yes, but I defined some AKs in position space as well. The one that
Okay.
diagonalizes the Hamiltonian is in momentum space indeed.
Mhm.
This is what you're getting to is I'm intentionally using this example because this example is a core example of quantum field theory. You'll see that when we second quantized like quantum field theory, relativistic theories, in momentum space, things are diagonal. The Hamiltonian is diagonalized in momentum space, so this structure copy paste generalizes.
Mhm.
Right?
Mhm. Okay.
What you're just saying is actually translates to the fact that the vacuum of quantum field theory has infinite entanglement, but that's literally what it translates to. But anyway, relativistic quantum field theory. All right. Any other questions?
Yes, Professor, one more question, please. Given that we have an infinite range of momentum values, which is not the case here, but given the fact that we are headed that way, how is the global vacuum state defined in that case? The tensor product is taken over a dense space?
Very good. Yeah, no, yeah, sure. Well, don't worry about it for now. Yeah, that's a very good question. We'll get there when we get there. But let me give you a quick answer. The quick answer is that we're going to be talking about massive theories, and the massive theories always have a gap. So we'll talk about that. If that doesn't say anything, just wait until we get to the.
Okay, thank you.
Yeah, sure. All right. So what are the key lessons that we learned from this example? The lesson is what I was advocating before. We start with a bunch of UV particles, and in the infrared, we get emergent quasi-particles, in this case, phonons, that were not included in the original theory, and these are collective excitations, and they have very different physical properties. For example, the UV particles are distinguishable atoms. The IR particles are indistinguishable bosons. The UV particles are non-relativistic, and as we'll see that low energies, these are relativistic. I'll comment on that in a second. So at low energies, these phonons propagate with the speed of sound, and they have a relativistic dispersion. What is a relativistic dispersion? Is that clear what I say? Non-relativity, non-relativistic versus relativistic. It's just this, that energy as a function of k is proportional to k squared, whereas with relativistic dispersion, energy is proportional to k. Good? Is that clear? What is this dispersion? Does this dispersion ring a bell? This is dispersion for a photon, right? Or phonon, hence the name phonon, right? It's a massless excitation that propagates like that. Okay. There's another thing that was interesting about this dispersion. There are a couple of things that are interesting about this dispersion relation. First is that there's a maximum energy for a single phonon. So I also invite you to think about the discrete translation symmetry and how it's related to bands of allowed energy. But yeah, I think these are the words that you might have already seen in quantum mechanics, or maybe if you've taken any solid state physics, this should look familiar. The continuum limit is the limit of epsilon going to 0. In this limit, it's important to notice that Emax goes to infinity and the dispersion becomes continuous. This is the regime that we zoom in here. In this regime, we recover a truly relativistic particle. The phonon is truly relativistic because the dispersion is linear with k. All right, so let's talk a little bit about this emergent Lorentz symmetry in the infrared. So for k epsilon much less than 1, we had this dispersion relation, right, which is relativistic, and the equation of motion for the phonon field, right, the phonon field becomes like this: del t squared minus v squared nabla squared. This is just omega squared minus omega k squared. It's the same thing, right? Phi of x of t, I just called it now phi of x of t, the field I was solving for. And it's convenient to write it using Lorentz notation, using covariant notation, del mu of phi of x of t. But we do know that this is not Lorentz. This is Lorentz symmetry where the speed of light is replaced by speed of sound. So here's a thought. Could it be that the relativity that we observe in our nature at high energies is also emergent because at some very, very high energy physics, something else is going on? Could that be? This is just something to think about. All right, guys. At very high energies, the lattice breaks the Lorentz symmetry, of course. So phonons are real. I cannot stress this enough. This is not just like some calculation we were doing and like, oh, maybe we're just sort of played around with a bunch of variables. When you take a solid and you look at its excitations, you could design experiments that actually will tick every time a phonon is that could measure single individual phonons, and every time it's measured, it could make it tick. You could make it very clear You could measure their momentum, you could measure their energies, and you could see them. The one very clear evidence of them is that if you look at the spectrum of a solid, it's discrete, and then there are sharp absorption lines at these energies. This is the clearest, this is the smoking gun evidence for a particle, right? So these are real, genuine particles. Phonons are particles. Any questions?
Yes, Haniba, as you said, like at very high energies, the Lorentz symmetry is broken. Can you elaborate on that?
No. In this model, Lorentz symmetry is something emerging in the low energies. Of course, the lattice itself, or the system of atoms, didn't have Lorentz symmetry to start with. It's an approximate symmetry in the infrared. I just said that think about whether it would be possible that in our universe, Lorentz symmetry is also emergent.
Okay.
That was just something I said. Just poking you guys to think about these examples are meant to make you think about, to tell you about the structure, a bigger picture, right? All right. Anything else? All right. So next, we can discuss interactions. So what we just solved was the quadratic equation, right? We linearized the potential. Sorry, we expanded the potential. The linear term was 0. We kept only the second order term. The whole thing was Gaussian. We diagonalized that Hamiltonian classically by Fourier transform, and we solved it, right? Because it was quadratic. This theory had particle number conservation, right? AK dagger AK is conserved. It has to do with the fact that the phonons do not self-interact. Actually, yeah, let me separate these. Our phonons at this level did not self-interact. They propagated freely in the solid, right? You saw that the Hamiltonian split into a bunch of the physics of the system was a bunch of sound waves that propagate freely. They don't interact with each other. Each of them propagates with a different frequency. Okay, but they don't interact with each other. They just propagate freely, right? So the phonons do not scatter. If you send a wave of a particular frequency, which is a phonon of particular energy moving in this direction, and a phonon of another energy moving in this direction, they'll just go through each other. Good. So now we want to include higher terms in the expansion of the potential. So in the potential, we took the lambda q squared term. Now we could have a q, we're going to keep the q cube term. For example, there are some problems with keeping only this term and not higher order terms, but let's ignore that for now. So this is the Hamiltonian of the quadratic piece. The Fourier transform, because the Fourier transform is nice for diagonalize this part, but it no longer diagonalizes this in the presence of the interactions. So the interaction now couples 3 phonons of different frequencies. Now they talk to each other, right? So they're coupled, which means that if once you quantize the model, what you're gonna get is you're gonna get all sorts of terms. You're gonna make Q and P, promote them to operators. Q, if you recall, was related to A plus A dagger, right? So when you expand them, these are A plus A dagger, A plus A dagger, A plus A dagger. You're gonna end up with terms of like this. These two guys, this is like this annihilates a particle momentum K3, instead creates a particle momentum K2, particle momentum K1. The momenta have to sum up to 0. However, the particle number is no longer conserved. This changes the particle number. By how much? This increases the particle number by 1. Right? Annihilates 1, creates 2. This term, same thing. This term removes 3 particles. This term removes 1 particle. Right? So the interactions, once you include the interaction in this simple model, particle number is no longer conserved and phonons can interact. All of this is encoded in this initial model, right? But the structure is all low energy emergent. So the low energy physics, when we kept only the quadratic term, showed the this mode propagating freely and it was not self-interacting. The particle number, phonon number was conserved, but in the presence of interactions, it wasn't conserved. Good. So now in the remainder of this lecture, I'm just gonna talk about the continuum limit because that's the direction we're moving towards. And this is actually the last time I talk about the lattice model. The remainder of this course and the next semester is all going to be continuum limit. All right, so how is this related to the continuum limit? Remember the classical equations of motion. I is the site index of Q that we're gonna replace it by a continuous variable X and we're gonna take epsilon to 0. The limit of epsilon going to 0 of Qi plus 1 over Qi becomes del X of Q. Sum over J of Fqj becomes epsilon integral of d of x, f of q of x. So sums are replaced by integrals at the cost of this epsilon dx. Right? Because epsilon dx is, so this is a Riemann approximation to an integral, and each step of it is epsilon dx. Right? So pi is mq dot I. That's just the definition of canonical conjugate momenta. We're going to define the field phi to be square root of lambda q. What was lambda? Lambda was the tension of the spring constant. With these change of variables, your Hamiltonian looks like integral of half del t of phi squared plus del x of phi squared. And as I was saying, I've said many times, when these displacements are small and there are many such sites, what you're dealing with is this continuous field fluctuating. This is a field theory. This is actually the simplest field theory we'll be dealing with. This is a Klein-Gordon free scalar field. We already quantized that basically, but I'll do this covariantly and nicely. Here I cheated. Can anyone say what the cheat was? In between these two terms, there should be a velocity term. That's the speed of sound. There should be, right? I set it to 1 so that you don't worry about it. Right? And the relativistic notation, we set the speed of light equal to 1. Here, I should have included the speed of sound here. We just set it to 1 to just show you that the structure that emerges like that. All right, so what are the quantum scalar fields? You have an x hat of j, this is the position operator. You have p hat of j, is the canonical conjugate. You can relate them to AK and AK daggers. Using all the equations we've had, there will be a zero momentum mode, there will be the zero modes. You define a field operator, square root of mu of x, and here are your field equations. These are equations that we're going to come back to later on as well. So in the next, actually, it's going to be halfway through the course because we're going to stick with classical field theory for a while. But phi of x and pi of x, this is the, remember, maybe I mentioned this. Yeah, I said this in relativistic quantum mechanics, and in quantum field theory, x is not an operator. X is a variable. The field is an operator. Here it is. This is the canonical conjugate. These are the operators. Right? X and t are just variables. Any questions? Any questions? So a little bit of terminology, because I'll be using this terminology a lot. The low energy free scalar field that we found is called an effective theory. It has a regime of validity, like any other effective theory, like any other theory of physics. Its regime of validity is the long wavelength physics and breaks down in the UV as a predictive theory of solids. In the UV theory, this lattice, the scale epsilon that separates the initial degrees of freedom, acts as a regulator. Once you start probing energies that are inversely proportional to a regulator, you start resolving you start seeing the UV degrees of freedom. The phonon picture will fall apart, and you will notice that the fundamental degrees of freedom are actually atoms sitting at these sites. So the phonon description is only true at low energies. And if you have large enough energies, you'll observe the lattice sites. Now, there's a subtle lie here. If the theory is completely Gaussian, and I do not take a continuum limit, the phonon theory with discrete momenta is exact. But when I do take the continuum limit to get honest to goodness fields, then I've actually lost all the information of the UV degrees of freedom. So again, just a provocative question. Are the quantum field theories of particle physics, such as electron field, proton field, are these effective field theories? Maybe yes, maybe. Well, the answer is yes. There are effective field theories. And that is why every time in this course, for the remainder of the course, we talk about quantum field theory, it will always have a cutoff. It will always have a regulator. It will always have a momentum scale that we call lambda or 1 over epsilon that will tell us where this effective theory breaks down. We will come back to this in part 2 of the course and next semester and explain renormalization group. And we describe the dependence, how the theory changes as you change the cutoff systematically using this language that's called renormalization group flow. But for now, the lesson to keep in mind is that every time for the remainder of this course we talked about quantum field theory, we will always have a regulator. Keep this analogy in mind. Any questions? This is the end of this lecture. So the job of the regulator is to provide a maximum energy mode, meaning that you see here, there is no mode beyond this energy. So it regulates your theory. Any questions? So what did we do? Let me just summarize. We started with a model of a bunch of atoms attached by springs, or particles attached by strings around the circle. We solved this classically. We found a bunch of, in low energies, we found a bunch of waves. These are the sound waves. Then we quantized it. We saw that the sound waves, due to particle wave duality, correspond to a bunch of quantum particles called phonons. We constructed the Fock space, the multi-particle quantum field theory that describes these phonons. We saw it has a vacuum, which was just a direct tensor product of the vacuum of each harmonic oscillator. That theory became a bunch of harmonic oscillators. Then there was a one particle Hilbert space. There were two particle Hilbert space. That we saw that these quasi-particles, phonons, are bosonic, right? So they're indistinguishable, and their wave functions should be symmetrized. We saw that once we include interaction, it will induce scattering or self-interaction between phonons, right? But for that, we have to go to higher orders. Most of this course is going to be about going to higher orders. That's where field theory is non-trivial. Otherwise, the Gaussian part, the quadratic part of quantum field theory, we just solved it. Then we comment on the continuum limit. All right. Any last questions?
If you like can only see the particles, how do you know how to write down the field? Does that make any sense? Like in our case, like we started with the field and then like we derived the particles, the particle portion, but like in most cases, like in everyday life, we see particles, right? So how do we know what fields govern them?
Very good. So we'll describe this. The whole course is going to be about that. So maybe I can ask the question differently. You could ask the question differently. You could ask, okay, so let's say you see the electron particle, right? So we said in the last lecture that the electron particle, this particle number cannot be conserved because it's relativistic. The theory is relativistic. So let's define an electron field. Right? Now, this electron field might not be fundamental, might be emergent. That's okay. So turn this around. Imagine this story that we just described, seen from the point of view of a low energy observer who doesn't know about the atoms and these springs. What do they see? They see these phonons propagating, the same way that we see, like, for example, electrons propagating. They see that the particle number is not conserved. So what's their natural thing to do? To postulate a phonon field and try to quantize, build a quantum field theory of phonons. They would be correct up to the regular energies that become, compared to the regulator, epsilon, 1 over epsilon. So they can build an effective field theory the same way that we build an effective field theory called Sano model of particle physics.
I see.
So we are in the same boat as the low energy observer that describes here, that sees only phonons.
I see.
Any other questions? So just for people, in case some people came later, there won't be a lecture on Thursday because I'm on a flight back. And once again, I apologize for the first 2 weeks being on Zoom. Starting next week, next Tuesday, we're going to be in person. And I'll also try to coordinate office hours. The first homework will be posted next week. And yeah, there will be more, hopefully, interaction than just the Zoom is not the right medium. All right. The videos are going to be posted on YouTube as usual, and the lecture notes are going to be posted on my website. Any last questions? If not, thank you so much, guys, and have a nice day.
Thank you.
Professor.